Okay, first things first. One, we're going to talk about machine learning. We're going to talk a little bit about deep learning, because machine learning in general is considered to be kind of a like branch of artificial intelligence. And so deep learning is considered to be a sub branch of machine learning. Some people ask me what NLP is. I've seen NLP placed in different places, but NLP, artificial intelligence, is a sub general of like computer science. NLP is a mix of computer science, linguistics, and arguably like machine learning, right? Techniques applied. And so NLP kind of fits within the machine learning rubric because it's mainly about syntax and semantics. I don't think we're really going to talk about NLP's role, but like consider it to be have some toes into the machine learning arena, particularly because of the semantics and syntactical kind of outcomes. And then we're going to talk about the ML pipeline, some general kind of use cases, and then you're going to get an idea of your projects. And then after this, we're going to do just a brief summary, do a little knowledge check, and then we're going to roll into some specifics around SageMaker itself. Okay. Since it is about 10:30, we'll probably finish this module and be halfway through the other module before we come back. All right. So to explain machine learning best, let's just take a look at like a common use case. So in this particular case, product recommendations, which was probably actually my first exposure to any kind of machine learning was back in 2013, 2014, making product recommendations. Now, I don't know how many of you were involved in machine learning back in 2013, 2014, but it wasn't as good as it is now. So it wasn't as cost effective. Certain algorithms like XGBoost and whatnot were not necessarily available. It was a slightly different ball game, a lot harder and very difficult to execute, right? So the classical approach, which by the way was my first approach, was basically that someone hard coded a rule, and I worked for God, what were they? They were like an advertising site, basically. You fingerprinted people across the web. It was my first and last foray into the advertising industry. And the rule was that if someone had if someone had bought this item within like the last 30 or 60 days, I think it was somewhere in that time range, it would basically just blob out a bunch of recommended items to them that we had inventory for. It wasn't really machine learning because it hadn't really looked at like other data, and it hadn't really learned how to analyze the problem. It just had a rule that said, hey, if the person has bought this hat in the last 30 or 60 days, show them other hats that maybe are of different color or have the same characteristics. And a human being, hard coded that into the thing. And it did not learn from prior data. It did not learn specific brands. It did not learn colors or characteristics or sizes or winter hats versus summer hats or baseball caps versus. It did not learn any of these. It was all created by a software engineer based on factors like business requirements and domain knowledge. By the way, that is still a totally legit way to solve the problem, right? Programmers set explicit rules. Now in this case, they were somewhat clear about how to generally make a recommendation. They were like, well, if the person's bought a hat, let's recommend other hats. Maybe they have a hat thing, right? And the problem with that is that it wasn't adaptable to actually truly understand, like based on the data, what the customer was actually interested in and what they were doing, right? And each rule that you added, like if for example, you had 1,000 items, the customer, you had to basically evaluate 1,000 rules to find out, well, if the customer's purchased this, then do this. If the customer's purchased this, then do this. And you're just evaluating 1,000 rule sets, right? And, because people are unique when you get down to these level of details, you couldn't use other customer data to necessarily infer per se, just using a rules-based approach that this new customer was actually interested, because there was no characteristic similarities. There was no dimensionality to how we analyze the features. We didn't actually do any kind of analysis. It was like, well, if this is true, do this. All human coded, right? Now, machine learning takes a slightly different approach, which again, this is still a totally valid way to solve a ton of business problems. It's not like machine learning is the answer to everything. That's like saying AWS is the answer to everything. It's not. Right? So here with the classical programming approach, right, you're doing purchase history, you're doing hard-coded human rules. With machine learning, what's happening is that you're taking that purchase history for that individual and all affiliated customers, plus a variety of other data that could be relevant to the problem. And you are feeding it through a model that's basically training itself in a way, right, to find patterns in the data. And the job here is to make a more precise, a more well-informed, a more accurate, even a more adaptive prediction. So in this case, we'd use like the customer's purchase history in combination with all of the customer sales data and everything that was running site-wide. And we would use machine learning to identify the patterns between past customers and sales. And we would apply this, for example, to new customers that we had never seen before, but we might have some characteristics of those customers, like their age, their general location, right? Male, female, gender, that kind of thing, right? We might do that so that we can basically infer what this customer, make an inference about what this customer is going to do. So that's the machine learning approach. So you derive rules from the actual data. So I sometimes jokingly refer to the data reality. What is the data reality? What does the data tell us about the customer? If our outcome is to figure out what new customers will purchase, we can look at similar customers who have similar characteristics and similar profiles, and we can make some inferences. These are probabilities, right? We can make some predictions about what they're going to do. So then all this training, by the way, like putting all this data inside the model, trains the model to emphasize certain characteristics or features of the data set to help with its predictions, right? And so, and by the way, you can continually retrain the model, as you probably know, to adapt to new data and the old data. And then together, you can just have a continually evolving profile as the customer evolves. Because at the very least, one thing you know about all customers, and all customers will age, right? Now, businesses are different because businesses can evolve and can age, but they don't do it as fast as people do, really, right? Unless you're Netflix and you want to reinvent yourself 3 or 4 times. Kind of waiting to see what Netflix reinvents themselves as now, right? Just as a side note, right? Remember they were provided discs and then they become streaming and then they did original content. What is Netflix going to evolve to now, if they're going to evolve at all? So the deal here, right, is that you can just train models ahead of time, saving time making towards future predictions, because you can train it and then apply it to new situations as they arise. And as long as you keep monitoring the accuracy, precision, and other values, whatever metrics you want to use that are important to you, of the metric as it runs in production, you can basically avoid the decay. There's a word for that, but you could avoid the decay of the model as it's in production by retraining it and refreshing it. So a model, as I referred to, is really just a trained algorithm, right? It's used to identify patterns in your data, and it doesn't really require explicitly manual set rules, but it does highly depend on both the business problem and the machine learning problem subsequently that you're trying to solve. So the key here is that this is an algorithm that is trained through the machine learning process, and it isn't created manually. And so let's look at a simple example here. By the way, I know that for you mathematicians out there, you're like, oh my God, this is really simple, Michael. What are we doing? Just bear with me. Remember, this is a primer class. We're not going to dive deep into statistics and mathematical formulae, right? Here's an example algorithm, for example. The blue items are weights, sometimes referred to as parameters, right? This is like the significance of the feature, which is the pink / reddish purple, or some people give me grief about that, but it's like the X0, the X1. It's like the features, by the way, are like a dimension of your data, a feature of your data. It's a characteristics of your data. For example, in this example here, X0 in our formula is a binary classification that says, is this product a hat? It is a hat. Well, then, okay, so yes equals 1 here. And And by the way, these features have to be expressed mathematically because we're dealing with computers, right? So what happens here is that, let's say, like for our first feature, like my earlier statement about making a recommendation about hats, is this product a hat? Oh, cool. Okay, yeah, it's a hat. And then what happens is that, let's say that we've taken our like first portion of this formula and said, you know what, that first part of that formula says, is this a hat or no? And then what happens is we're going to ascribe a weight to it. How much does that feature affect the accuracy of the prediction, like how good the prediction is? Now, what's interesting here in this particular case is, let's say that hats make up 80% of the purchases that this particular customer's made. Like this particular type of customer, right? In other words, there's a bunch of like characteristics about this customer and this particular customer, 80% of the time, I'm sorry, hats make up 80% of the purchases this customer has made. So we're gonna put a heavy weight on this. We're gonna put a 0.8, right? And this represents like how important the associated feature is to determining the accuracy, or the, like, in a sense, the goodness of the prediction, right? So something that has a higher like influence on the accuracy is going to have a higher weight. So let's say this model has been trained and that blue parameter has been denoted as being, well, yeah, it's going to be 0.8 for this because this whole class of customers that we trained, definitely 80% of the time they purchase hats, right? And then maybe for the next set of evaluations that are inside the formula, we might say, hey, is it from this brand, right? For example, let's say it's like a Gucci hat or something like that. I know it's horrible, but I just would pick something in common. Let's say it's a Gucci hat, right? And so this time though, we find out that they're only like 0.25 likely to purchase this brand. And then maybe that keeps going. Maybe there's other brands that have higher weights. And so in this particular case, let's say it's just like about a quarter of the items this bought were this particular brand. Now, if we just don't have other dimensions, like other like portions of the formula that we're like modifying and evaluating, which this is like really simple. So what would happen is that we would have a threshold that says, look, if it's a, if it's a 1 or above, let's go ahead and recommend this item. And so we would do the math, or sorry, the model would do the math, and it would come back and say, look, we're going to make this recommendation because we're above our threshold. Because it didn't have to be above 1. It could be 0.95, it could be 0.9, it could be 0.85. It just depends on what the business and the ML model, the problem, are defined as. So this is where you would come up with a recommendation. So if it's above your threshold, then it's like, we want you to make the recommendation. If it's below the threshold, you might say, no, I don't want you to make a recommendation because it's not accurate enough, or it's not good enough for our business needs. So that's in general how the math works. This is a rabbit hole you can go way deeper down, and I know some of you have, right? But in general, that's what we're looking for, is we're looking to basically identify the characteristics of the data set that we can influence the most, right, in terms of weighting, that will give us the most accurate prediction in this particular case. In this particular case, right, it can change. So then the other question then is, okay, so good, Michael, that's a little sample of like like very simple algorithm that could be used. What kind of algorithms are we talking about with machine learning? Now, there's like 14 types of machine learning. The last time I looked at it, like everything from like deductive and inductive learning and semi-supervised, and there's a lot. These are like the kind of like top 3 kind of categories that are commonly associated with machine learning. And algorithms that fall into this place fall into one of these like general 3 buckets, but just know there's a lot. There's like 14 of them. And NLP is not one of them, by the way. NLP uses a bunch of machine learning techniques, but this is just within the machine learning branch in general. There's supervised, unsupervised, and reinforcement learning. And this is going to cover a lot of use cases for most businesses, right? So supervised learning, by the way, is a model where basically you have a teacher that says, hey, this is a good prediction and this is not a good prediction. Like, like the outcome. So you're using a data set where what the like for example, customer did, you know whether they purchased or not. So in other words, your targeted outcome, also sometimes known as the label, is actually in the data set. You actually know like how the data leads to the outcome and what outcome it leads to. You know whether the data actually leads to a purchase or it doesn't lead to a purchase, right? In general, that's a supervised set, which we'll talk more about in a second. Unsupervised is where mainly for like clustering, anomaly detection, density analysis. This is where unsupervised falls in, right? And again, we're going to dive into this a little bit more. And then reinforcement is where you've got an agent in a controlled environment and you want them to learn based on a kind of a reward system about how to achieve an end goal, but you don't really know the means to get there. You just want to get to the end goal. Again, we're going to talk about this a little bit more. So let's talk about supervised first. So supervised, as I mentioned, is that you learn by identifying patterns in a data set that's already been labeled. And what do I mean by a label? A label means that one of the features of that data set is the outcome that you want to predict. So, you know, this is super popular because it's widely applicable. And it's called supervised because there needs to be like a supervisor or a teacher who can show you what the right outcome is. And you use that data to train the model to figure out what the right outcome is. So it learns by example. So like, for example, here, you've got pictures of cars. And by the way, these pictures have been labeled by people, which, you know, 95% accuracy, give or take, right? I know that sounds silly. It's like, cannot everybody identify a car to 100%? Anyway, we're going to move on to that. So here's the car and another picture. Can you tell me if this is a car or not? Right? And let me be clear. It's a picture that it's never seen before. So it's not labeled as a car. It's just a picture of an object. Can it identify that that's a car or not? And so you can see there with the prediction, it is like, oh, hey, I put a bounding box around this. The car is right here. This is a car. So what happens is you train it with data where you know it's cars, right? And you might also have some data in there that you know are not cars, just to say this, right? Especially if it's like a camera, you might train it with a bunch of data that shows transportation data, right, of various types. Anyway, regardless, transportation pictures. And then what would happen is then after the model was trained, you would then give it a new picture that it would have no idea. There's no label on it that says whether it's a car or not, and then it would identify it as a car. That's the like the most accurate outcome. It could also say there's no car in the picture, right? Now, in general, there are 3 types of supervised models, right, that can be used, right? They're mainly like kicked out into 2 categories. There's classification, like algorithms, if you will, and then there's regression problems, right? So think of ML problems as falling into generally these 2 categories. You're either doing a binary classification or a multi-class classification, or you're doing basically like a numeric probability, really, somewhere. You're doing a regression problem at that point. Yeah. So binary does basically, hey, is this fraud, not fraud? Is, you know, right? Identifying like yes or no kind of questions, 1s and 0 kind of questions. Multi-class, for example, would be, hey, what kind of object is this? Can we label it in some form or fashion? For example, you could take unlabeled data, right, and have it classify it in some form or fashion. In this case, I think the example they use here is that they have a user, and based on their most recent history, can we route them to a person with appropriate skills? Like, is it a support problem? Is it a returns issue? Do they need to go to accounting? You know, based on different like profiling. And then a regression problem is like you're trying to predict the outcome of some kind of basically number, right? It's like predicting, like, for in this case, it's like stock price. So that's supervised. Regression problems and then classification problems are the general way that those are divvied up. And we're going to talk about the specific algorithms that go underneath those, particularly when we get to the actual model piece, right? By the way, I saw some notes in chat about Google's getting users to label data with the am I a robot authentication process. There are lots of them actually that sneak that in as far as label. Like Duolingo for a long time would do that a lot, right? Particularly on the NLP side of things. Is that there were Memrise was another one that did that a lot, where you would play a game and you thought you were learning, and you were, but you were also like reinforcing data labels basically for them. Now, unsupervised is a little different because the outcome you want to predict is not necessarily in the data set. It's not labeled, right? And so what happens is that this is where you're taking algorithms that are looking for either like clustering, like aggregation, which is just a variation of density, or you're looking for where data is clustering and you're looking for the people who are not clustering. Like you're looking for the data points where the data is kind of an anomaly, right? It's not fitting the regular pattern. Now, what's interesting about this is that, you know, you can detect anomalies, but remember that just because something is outside of the normal pattern doesn't necessarily automatically denote, for example, that it's bad, or it might be some kind of domain context that you're not actually familiar with. So for example, that cluster of failures on the upper right hand side where all of a sudden there's speeds of up to 175 miles an hour, maybe there was a racing day on the street that day. I don't know, right? So, but with the point is that with unsupervised learning, models can identify what are just simple outliers and what's more likely to be like a result of a hardware failure, and how things cluster and how things are dense together. The other thing that's interesting about unsupervised learning is that, you know, we use language to describe objects in reality most of the time that we either, you know, see, hear, or experience through one of our senses. You know, taking computer vision as an example, it's surprising how accurate unsupervised models can actually take a bunch of pictures. And for example, they'll group all the dogs together, and they'll group all the cats together, and they'll group all the birds together, like, you know, give them pictures of like objects, and through like analyzing edges and corners and coloration and like they'll be able to pick out the common like objects, and they can cluster those together. So even though they don't know, for example, that it's a bird or a dog or a cat or whatnot, they can still cluster these unlabeled items together with a, you know, a really interesting amount of accuracy, right, and consistency. So what unsupervised learning is when you use with data sets where you don't actually have the outcome, the targeted predicted outcome in the data set. Notice, by the way, that's like here, they're like, these are false positives, right? Which means, right? And then these are true positives, like, oh, we're having a hardware failure here, right? In that particular case. You'd have to dig into that a little bit, by the way, right? Oh my God, all of a sudden we're going 200 miles an hour. Is that really happening? Are they really doing that on surface streets? Then you might go look at a picture of the data. Hey, there's no car there. A bird flew by, right? So things like that for further analysis. Okay, so if supervised is with labeled data sets and that acts as a supervisor, and unsupervised doesn't have labeled data sets but can still be used clustering and density and outliers and that whatnot. Reinforcement learning is really like trial and error style learning, right? It is ideally done when you're in a relatively constrained environment, although it is surprising how well these things can be figured out. But it basically, this one continuously improves the model by basically mining feedback from previous, in a sense, choices and the results of those choices. So you've got an agent in a controlled environment, and I think they have like the Deep Racer here. This is one of the best ways, is that, you know, the car can go forwards and backwards, it can turn, it can increase speed, it can decrease speed. And the goal is that it's trying to go around the track as fast as possible. Obviously a wreck is going to slow it down tremendously, right? Either going off the track or hitting another car, right? Or skidding, sliding out of control, that kind of thing. And so the goal here is that it basically tests all the choices it makes and gets this like feedback mechanism about whether that was a good outcome that it wanted towards the goal, or whether it really wasn't ideal, right? Because like we wrecked or we went off the track or some variation thereof, right? So the car is going to learn in this particular case the desired driving behavior to reach the goal of completing the track and as fast as possible. And so it might start by just trying to complete the track, and then it might make some different experimentations to see if it can go faster around the track. Does it need to hug the inside corner? Can it hug the outside when it's coming in? Like, and this is from AWS's Deep Racer, which I think they're still running this actually. The Deep Racer League is still going on, if I remember correctly. I participated in this 2 years ago. Tons of fun. The little car is a little weird because the camera's actually on the front and the back slopes down. So the bulk of it is actually in the front of the vehicle. It's a little strange. I think you can buy them for like $1,000 or something. So again, you have an action, and the outcome of that action is evaluated. Does it get us closer to the goal, or is it like going to hurt us, right? And so as the agent moves within the environment, its actions are going to receive more and more rewards and fewer penalties until basically it meets the desired outcome. So it's going to experiment to see if it can find out how to get closer to the end goal, which is kind of cool. So supervised uses labeled data, unsupervised uses unlabeled data. Reinforcement learning is an agent in an environment where it basically has feedback and penalty systems, a reward and penalty system in order to figure out how to make the best possible choices in that environment to achieve the outcome, right? Whatever the outcome is. Now, AI, so machine learning fits inside of artificial intelligence, right? And then deep learning kind of fits inside of machine learning. That's probably a good way to think about it. Oh, yeah, there's a diagram. So we're going to go just a little deeper in for a second, is that deep learning is really a subset. And so what's interesting is that deep learning, functions similarly to machine learning, but the difference is that we have these artificial networks that are created, right? And the complexity of the problems that can be solved and the hardware constraints that are applied to deep learning are going to be a lot stronger, right? They're going to be a lot more complex problems can be solved because basically hardware is starting, and the way we use hardware is going to catch up. Now, if you think of artificial intelligence, is that a machine that can just like play chess based on the rules, but it doesn't really have any necessarily like real kind of skill or intention because it neither has nor the history, and it isn't really trained in any particular way. And then you've got machine learning, which is where we basically teach the model how to play games by feeding it in all of the past games that have ever been played, right? And so it could be simple chess strategies. And then, for example, it could use reinforcement learning to identify patterns that are more likely to give you winning moves, right? That's a possibility. Now, with deep learning, what happens is that you basically, in deep learning, you have these mathematical layers, these neural networks. And what happens is that the machine learns how to play chess by basically playing against themselves. And so they are not constrained by human viewpoints based on past data. They will explore every single possibility and discover new ways to do things because they're going to basically try every single permutation and rule that they can. Not every single one. It depends on how you scope it. But the point being is that it's a layer-based approach. It's an iterative-based approach to learning chess strategies and can recognize patterns that are like way more complex than what you can do in machine learning. So if classical programming is just rule-based and machine learning is data with an algorithm trained, right? And then of course you can always obviously put new data in for predictions, right? Deep learning basically, in a sense, uses like these mathematical neurons that are layered together with inputs and outputs, and they just chain together. And it basically performance data in the model is just continually trained. So the features about the data are typically derived by the artificial neural network itself. During the training and the tuning process, you're not really using like supervised data as an example. So the model is then fed back through the artificial network iteratively and generating a finer and finer and finer model. And that can be a continuous process. So here, these models for artificial neural networks can be trained on raw data, right? And so it does its own feature extraction about what's significant and whatnot based on the outcome you're striving for. Now, the concept for this, by the way, has been around for a long time, since like the 40s or 50s. It wasn't really until 2010, really 2015 actually, where ANNs started to be used in real environments, right? And to say this is that each layer of those like purple dots there, think of it as a mathematical like input or function that has outputs that then feeds the next layer, that feeds the next layer, that feeds the next layer. And notice how it constrains down where it finally produces an output or prediction. Because what it's doing is it's basically deriving features about the data by doing its own mathematical analysis. And you can do many iterations and many runs of that data through it as it learns more and more and more. Here's an example. Here we've inputted a rather cute picture of a dog. It starts by identifying like specific features, like maybe the first layer is going to learn the edges, right? The next one is going to learn what kind of shapes and corners do we have. And then the next one is going to do grouping around parts. And that process keeps refining and refining, perhaps even getting more granular in terms of like the goal, until finally it can say, hey, that's a dog. And remember, since it can examine these pictures pixel by pixel, it can really find contours, edges, corners, patterns, coloration patterns, black and white patterns, dimensionality patterns. It can find like from hue and saturation and whatnot that we really can't do at that level. I mean, some of it we do instinctively, but we can't operate at that level of granularity. So it can easily identify patterns that the human eye can't really see, as an example. So this would be, image classification using an artificial neural network. Now, you may remember I said, hey, we didn't really see this like become super useful until about 2015. Notice that in 2010, as you can see there, we were at like 70-something% accuracy. This, by the way, is from the ImageNet Large Scale Visual Recognition Challenge. The 2010 was the first year of the challenge, right? So the idea here was that it's basically a challenge to basically improve machine learning's ability to mathematically recognize certain objects. So research teams basically submitted programs that classified and detected objects, right, in scenes and photographs. So 2010 was first one. Then we're seeing some improvement. This kind of keeps going. And then in 2012, thereabouts, basically what happened is that we had the ability to support artificial neural networks as part of deep learning, and the accuracy rate jumped up to about 82, and then you see it increase and increase. And then in 2015 is when we see it actually exceed, average human performance, right, from a single network. Now, these are narrow tasks, right? These are narrow tasks, but still significant. But now we don't need human beings to actually do this. We can actually have a machine do it. So the recap here basically is that deep learning uses artificial neural networks, which are these layers of mathematical inputs and outputs that are just layered together, that all are like identifying different characteristics and features of the data, and therefore using this unlabeled data, if you will, to kind of make their own feature extraction and derive the outcome that we're looking for. So it can be trained on raw features. It's a subset of ML methods. There are a range of different layers for computational efficiency, and you can have hundreds, if not, close to thousands of layers, depending on the size of the model that you're following. There's some art and a lot of science to that, but we're not really going to talk about deep learning here in this course, but you just need to be aware that it exists. There's actually a whole dedicated class called Deep Learning on AWS that is dedicated specifically just for deep learning on AWS. Let's see. I see that Mohammed posted a picture. Let's see what this looks like. That's good. Mohammed, that's good. Labradoodle or fried chicken. That's great. I like that. I've seen that before. Oh yeah, NPR. Funny. Thank you for sharing that. Good. All right, any questions about this? before we go forward? Remember, I said it in the beginning, by the way, the NLP pulls from NLP, natural language processing, is a subset of artificial intelligence, but know that it pulls from linguistics and computer science in general, and it uses machine learning techniques. So NLP, while you often see it in the machine learning space, is actually, and some people refer to it as a sub branch of machine learning. It pulls from a lot of different disciplines. So. I don't know that I could make that statement, Thomas. That's a great question. So you asked, is deep learning the pinnacle of our ability to solve complex problems through machines, or are there more complicated things out there? One, I can tell you for certainty, there are actually far more complicated things out there. Are they in mass use, like machine learning and now deep learning? No. But there are more complicated things out there, right? So I would say, like, from a mainstream perspective, this is the pinnacle. Deep learning is the pinnacle of what we can solve, but there are other things on the horizon coming down the pipe. So yeah. Yeah, exactly. Right. An aspect. Just to say this, is that the reason that this is becoming so popular is that it is becoming so democratized. So think about this, is like most of us don't really know exactly how to take a car apart and use a combustion engine, whether it's, a gas fed or electric. We don't really know how to do that. So, but we can drive a car and we can get all the benefits of driving a car. And so this is what's a little bit happening more and more with maybe machine learning, but not so much deep learning. But you see it happening more and more, is that it's becoming democratized, where it's a lot more accessible. You really just need to know how to drive the car and not necessarily peel back all the statistics and the math. Does that mean you don't need experts? Of course you still need experts, right? We still need someone who knows how to take the car apart and to go to help us. But that's the thing, is that right now, Thomas, for your question, deep learning probably represents the most accessible methods that we can use to solve these problems. Yeah. Quantum machine learning is going to be really interesting. Yeah. Agreed. Yeah, we do have a ways to go on quantum computing. Although we're not far from actually creating an Ansible, which kind of weirds me out a little bit because of quantum entanglement. Can't wait to see that, where that goes. Anyway, not necessarily an ML problem. Moving on. All right, so let's talk about the pipeline as it relates to this class specifically. So we're going to follow this in stages. And so the first part is that obviously you always start with the business problem. Unless you work for an R&D firm or at a new university where research is, just general exploration is supported, you're typically being paid by a business to solve business problems, or by a client who runs a business who wants to solve business problems. And so you're trying to figure out what business problem, with hopefully a domain expert or a business owner, is trying to solve. And then you are forming the problem, and then you are articulating your business problem and converting it into an ML problem. So business problem really should go into ML problem formulation. So we're going to get into more detail on this, but in general, we're just going to talk about like the steps. And then once you've got your ML problem and how that relates back to your business problem, you are generally going to start looking at data prep and pre-processing. And this could include things like data, like sourcing, collection, integrating your data together, some pre-processing, maybe even some visualization to kind of see, like, are you missing values in your data? Are there any huge outliers that are really going to skew and bias your model a little bit? Maybe even some transforming the data into different formats. So maybe it's in 5 different formats and you need it to all either be in JSON or protobuf, right? Or CSV. It's more likely. Sorry. Making sure that your data is formatted correctly for either SageMaker or your ML algorithm, and that your data is like cleaned up in a way, right? So that's data preparation and pre-processing. And then there's the actual model training, where you're going to train and tune your model. This is definitely an iterative process. It can be performed many times through the workflow. And because initially, by the way, your model is not going to yield results that you might be expecting. So you're going to have to do additional feature engineering and tune your model's hyperparameters, which are parameters about basically the algorithm itself and how it learns. You might actually do some feature engineering and add more dimensionality to your data. You might take dimensionality away. You might do some correlation aggregation and identify the most important values in your data and remove other values because they're skewing your outcomes, right? And that cycle of model training and tuning is also part of like model evaluation. So tuning sometimes fits more in model evaluation. It's like, how is this solving the business problem? Does it meet the business goals? No. Well, we might be going back and like train the model, a little bit more. We might change, do some feature engineering. We might do some data augmentation. We might do some tuning, right? It just depends on how you're not meeting the goals. So you might take a second look at your data and some of the features as for a way to improve the model. If it does meet the business goals and it's good enough, then you might deploy it. And you might deploy it either in what they call online or on-demand mode, or you might deploy it in batch mode. On-demand is where you submit like a single customer profile, for example, and get back a recommendation. Or you might do what's called batch mode and you submit 50 customer profiles and you get back 50 different recommendations, right? So it just depends on how what your business needs. Is it real time? It's probably going to be online or on demand. If it's something that you do like once an hour or once a day or once a week, it's probably going to be batch. Any questions about the general broad strokes of this pipeline?
Hi. Yes. This is Darshey. I have a question. Is this like related to inference types? That was one of the questions in the pre-assessment, and they had like an online inference versus batch inference.
Yeah. So inference is usually what they call it when the model is released into production. It's making inferences. So that's definitely related to it, right? If it's online, obviously it's single data point submitted and then real time you get the results. If it's batch, you submitted a whole set of data points, like for example, like a customer like profile, for example, and you're going to get like back a whole set of recommendations.
Oh, okay, got you. Thank you.
Yeah. You'll hear those words kind of used interchangeably, but usually once you've launched it in production, you're referring to inferencing at that point. Good. All right, so let's talk about some use cases. Because as you know, machine learning is the pinnacle of human evolution and is there to solve every single problem. You should always use machine learning. You should never use anything else. So, God, if I actually said that for real, you should run. That'd be horrible. That's like AWS is like the solution for everything, is it not? I am an Amazon authorized trainer, but I think they appreciate the fact that I keep it real. So ML is not a solution for every problem. Just remember, like if you can solve it in software with a few rules, that might be good enough for the business. They might not be interested in a more granular, more predictive model. It may not be worth the cost, right? They may not have the data, they may not have the capability. It may not be necessary because they're looking for something that doesn't require that level of specificity and granularity. But in general, if you can't code the rules and you want something that scales massively, then you're probably going to be using machine learning. That's pretty much going to be it. Now, the kinds of problems that can solve would be related to, right, categorizing things, right? That would be part of the supervised learning model. Predictive routing, which would be supervised in, let's say, multi-class classification, right? So being able to route somebody based on purchase history or general type of problems with that product that they've purchased in the past. Fraud detection, which could be a classifier, like a binary classifier, fraud, not fraud, or it could be an unsupervised program where you're looking for anomalies that don't meet the standard, right? Because maybe you're looking for standard transactions and You want to know if there's an anomaly that doesn't meet the normal pattern. Be careful with that because, you know, that might not be the best way to approach it, but could be valid. Personalizing advertising, where you're like making recommenders, right? Which could be everything from a regression problem to a, you know, some kind of multi-class classification. Voice assistants, where they're trying to determine like what you're asking both semantically and syntactically, mainly semantically, right? But syntax is important for determining that to a certain degree. And then dynamic pricing, which would probably be like a regression problem. Like, what do we, you know, what's the price going to be? Or do we like charge people different prices based on their history? What do you think the person's willing to pay? I know that sounds sketchy and nobody wants to be the victim of that, but people do that. Email filtering, spam, not spam kind of thing, right? Which can be classification. Self-driving cars, which can be everything from object recognition to reinforcement learning to a bunch of different aspects. And then customer churn prediction. How likely is this person to leave us based on our history with other clients and their usage patterns and their payment patterns and how they used our service, stuff like that. As an example, let's say that we're focused on the call center problem, which basically says, well, actually, a couple of years ago, you know, Amazon was trying to basically figure a way to improve how it routed its calls because people were getting, you know, to like people who didn't have the skills to help them. Now, of course, most of us just solve this with a menu system. Press, you know, 1 for returns, and 2 if you've got an Echo, and 3 if you got a Kindle, and 4 if, you know, you just bought something, right? You get the idea. So the customer will make a selection, then sent to an agent who'd be trained in the right skills, right? So they determined that the current routing system was problematic because there's so much stuff sold. It's like, is there a way for us to predict the list of things that customer might be calling us for so that even if they did choose general purchase, we might just know that they bought 4 lawn chairs from a third-party reseller. So we're going to get them to an agent who has third-party reseller skills, right? So otherwise, you know, they might have to end up starting with a generalist. And what they were trying to do is they were trying to reduce call transfers. Now, for Amazon, you know, for a lot of businesses, like that might not be a big deal, but for Amazon, who was dealing with hundreds of millions of customer calls a year, that small improvement in efficiency and getting them to the right agent who has the right skills to reduce transfers and handoffs and basically increase customer satisfaction, that was a huge thing for them. So they wanted to make sure that the customer, one, didn't get to the wrong department, which meant basically the call agent who didn't have the right skills to help them. So they wanted to reduce that. So the business problem was, how do you route customers to the correct agent? How do you route them to the right person? And so is there a way that we can identify patterns in the customer data when they, right, that we can use to predict what agent with what skills we should actually like route them to? In this case, since there's multiple classifications of agents with different skills, we're looking at a multi-class problem. So they wanted to base it on past data. So we know that this would be supervised learning based on where other past customers who had those same or similar purchases, where they ultimately got routed to. And so, you know, reconciling agent skill sets with the historical call records and perhaps like number of transfers and customer satisfaction, right? And then when the data, once the data was collected and when they got all the historical data, because they're moving through this phase, right? They got the historical call records, they got the agent skill sets, right? They looked at features of the data, like were they Prime members? What did they own? Did they own a Kindle? That kind of thing. Then what ended up happening is that there was some data analysis, right? This included cleaning up the data, taking a look, do we have the right data? Do we need all the features? Are there highly correlated features that we can drop or condense, right? So, you know, are there like labels here that you want to exclude from the model? So for example, they might have had, you know, instead of having labels representing specific, like multiple Kindle skills, maybe it just needed to be combined into just one Kindle label, so that every customer who had a problem with a Kindle would just end up routed to the agent trained in all of the Kindle issues, as an example. And then here, they went to data visualization where they like wanted to get a quick sense of like the total number of features and label summaries, basically helping you better understand the data they're working with. Now I gotta tell you, pie charts are not awesome for deriving math, but it looks like a third of that is return, right? Wait, is that right? Yeah, no, maybe maybe a little over a third is returns, and then maybe a third is prime memberships, and then a combined third is Kindle and miscellaneous. I probably wouldn't, if I was trying to derive numbers, I probably wouldn't put that in a pie chart, right? But like in this case, you notice that, and technically it's 40% was actually related to returns, little less than a third was prime memberships, and another 30% to Kindle, and the remainder, right? The point being is that this gives you a breakdown of like what people are calling for. Most of the time, it's returns. Second is prime memberships. Third is Kindle. Good to know. Why is this significant? Because especially if, like, for example, if you're doing like classification problems, you might have 99% of your data is like not spam. And then you got 1% that's spam, which we would all be lucky if that was actually true. And what would happen there is that you'd be really good at training your model to like identify not spam, but not necessarily training it to identify spam. So you got to worry about in your data set also like bias just simply from like the number of outcomes that are there. This actually might not be a bad skew or division of labels, but it depends on all the other features in the data set. So once you've got past pre-processing and visualization, then you actually do model training. Now, typically what happens is that you want to split your data to ensure basically a division between your training and your evaluation, and then what we either call your holdout data, sometimes referred to as your test data. Well, actually, people refer to it more and more as test data. Some people use holdout data a whole lot anymore. I don't hear that. This can be an 80-10-10. This could be a 70-15-15. Different splits, but in general, that's how people approach it. What happens is you're going to train your model and then validate to see how the model's doing. You train, validate, train, validate, train, validate. When you feel like you're really close and your model's like right there and you just want to do one final test or holdout evaluation, then you're going to take your test data and run it down. And this is where the model evaluation comes in, which is where you use like either 10-15% of the data to verify that the model is performing at or above the necessary business threshold, right? It could be accuracy, it could be an F1 score, it could be precision, it could be recall, like there could be other metrics that you would use, but you're basically saving that last data set to find out whether or not you're actually ready to go into production. How in a sense accurate by whatever way you define accuracy, not necessarily by the accuracy metric, to make sure the business problem is being addressed. So trainings, the whole data set is typically broken out into this kind of ratio: 80-10-10, 70-15-15, 70-20-10, right? It just depends. So then after evaluation, you might do some, like you evaluate the model and you begin a process of iterative tweaks to the model. This is where you might do something called hyperparameter optimization. Just so you know, SageMaker has automated hyperparameter optimization, which is kind of fun because it will actually either using Bayesian or random search, it'll actually go through and try to optimize a minimum amount of difference between the reality of the data and the predictions it's making, which is really cool. Yeah. This is like the things we would change, like the learning rate, bin size, like a bunch of different, there's a bunch of different parameters. I don't want to get too far into that. So Angela, it looks like you have your hand raised. Did you want to add something?
Hi, can you hear me?
Yes.
On the model evaluation page and the one before that, so this represents Amazon's recommended data split, because sometimes you see different proportions of training versus validation, and sometimes you even see different names for the two sets. So like sometimes there's just training and test. So I just want to confirm that this is like this is what Amazon is putting forward.
I don't think this is specific to Amazon. This is in general. This is an industry concept. Simple holdout. This is not. Amazon's not recommending 80-10-10 per se, but 80-10-10, 70-15-15, and there are different names. Sometimes it's the evaluation set versus a validation set. Sometimes it's test set versus holdout set. They're not necessarily espousing that ratio. That is a common ratio, but it is common to split the data into 3 data sets. So yeah. So are you asking, like, are they going to test you and say, hey, you need to use 80-10-10 or 70-15-15 as the splits? Probably say that's accurate.
Well, just I've seen different, I guess not necessarily the proportions, but the fact that there are 3 different sets rather than 2, for example. Like coming up, I've seen a lot of 2. I've seen a lot of splitting into 2.
Yeah, and I think it depends on how you're doing the validation. Like if you're doing like K-fold or cross-fold validation, what will happen is that you'll see the training set get mixed in kind of differently with the validation set. We're going to talk about that when we come to model evaluation, because it just depends on what validation methodology you're using. In general, inside the data set, the training set, something's going to have to be used for validation, right? Because otherwise, if you do that, if you don't actually set aside some kind of data or use some other methodology to do validation, you're going to overfit your model because it's not going to match reality. It's just going to basically memorize the inputs that it's seen, and it won't do outputs. It won't actually be able to analyze the relationships. It's just going to do rote memorization. So you might see it called different things, but in general, it is split into 3 data sets. If you've only got 2, that means you're probably using some other methodology to do validation that involves a portion of the training data set, right?
On the test, will we see different names for these sets?
You mean other than validation and test sets? No.
Okay.
Yeah. Every once in a while, you'll see validation shifted to evaluation, like set, but that's it. Test set usually they don't use holdout, for example. It's either training, validation, and test, or training, evaluation, and test. You don't see different names otherwise.
Okay.
Yeah. Yeah. Darche, Scikit normally uses usually training test. Again, it depends on what you're using for validation, right? So you're probably using some kind of form of cross validation to do validation against your data set. So, but we're going to get into all that, including how scikit-learn approaches that, right? And how to understand those concepts when we get to model evaluation. So it won't be till the 3rd day, but we will talk about it. Good. Yeah, and I will say that, yeah, make sure you keep asking questions like that, especially where it's deviating from like the labels that you might put on it. So that make sure that your associations are strong. So Angela, thank you for asking that. It's important because you might be like, well, I don't think I know what this is, but I have a different name for it. And then that way we can associate this name with the name you already have. That way you don't feel like you have to learn something new every time. It's just a different label for the same thing. Okay. So you got your model, it's training, you're taking some portion of that data and you're validating it, or you're taking random sets of the training set and splitting that out, like you're using like K-fold validation, right? And you're doing it that way. But I would say, like, generally everyone holds out some kind of form of test data to make sure that the model is actually getting towards the end goal. Now, by the way, you might have to shift your technique based on the size of the data set, like how sparse it is. And if it has like high dimensionality, or if you have a large data set with low dimensionality, you might have to approach it different ways, right? So yeah. So model tuning, by the way, after running a chaining job, what you're going to do is you're going to basically, and this kind of like folds in a little bit with evaluation, is you're going to run some iterative tweaks to control things like how fast or slow the model is, right? And there's lots of other dimensions of this. There's tons of hyperparameters that you can tune, both for the model and the data, and how you optimize learning, basically. So parameters for how the model functions, how the model learns, and basically the data inputs, you can tune that as well. Validation sets are used for mostly used for model selection. I don't know about that, Eric. That's an interesting statement. I'd be interested to see where you derive that from. Cross-validation is rarely helpful in production, giving non-stochastic distributions and data from your training set. I could agree with that, actually. Yeah, I would disagree though with the statement that validation sets are mostly used for model selection. I mean, they definitely can inform whether or not you're using the right model and getting the right predictions. So maybe actually that's true. Actually, let me think about that for a second. But I mean, also it's used to validate like whether a model is trending in the right direction. Yeah. Yeah. I don't know that you would just use it though, just to determine whether or not you were using the right algorithm. You would also use it with the existing algorithm and all of its iterations to determine whether the model was trending in general towards the predicted outcome. Once you felt like you couldn't train it anymore, then you would basically do a final test. And then that's when you then would do tuning with the test data, because you'd be at the lowest minima that you can get, or lowest error rate you could get for the predictions, right? So yeah. Yeah. Okay, good. Yeah, just make sure model. Yeah. Okay, model selection. Perfect. That's a good point. Yeah, because it'd be used for iterations. Yeah, so I actually do totally agree with that. Okay, and then like more model feature and turning, like feature engineering, right? Like for example, what was the customer's most recent order? I gotta tell you, date and time of most recent order. I mean, just raw like that probably isn't going to be useful. How about did the customer purchase in the last 60 days? Or what was the number of days since the customer's most recent purchase, right? That would probably be a good option to convert a feature into something a little bit more meaningful, right? So here we saw that, you know, on 2018 at 1 p.m. on the 13th of January, someone made an order. That's great. How long ago was that from the date that we're interacting with them? Because I got to tell you, if it's over like 120 days, probably not what we're talking about. If it's within 7 days, probably a high probability that we're talking about this product, right? You know, if we're within 24 hours, right? So, you know, you could convert that into different columns if you want, or features of your data set, or you could put a number in there that could be evaluated as part of it, right? And the lower the number, that could be put a higher weight on it, on the significance. And then it becomes like a much more helpful feature, right? Good. And then remember where we started, right? Where we were back all the way back here. Got the wrong department. Then we got to another tier. They weren't technical enough. And then we got to the correct agents. There were 2 transfers. The problem they were trying to solve is to increase customer satisfaction from their perspective by minimizing the number of transfers before they got to an agent that had the skills to help them with their problem. So this is where all of that took them, is that they wanted to land here by minimizing the number of transfers. Good. Good. Love the questions too. That's fabulous. Okay, so let's talk about this. Well, first of all, before I move on, are there any questions about how that Amazon call routing to the right agent problem, how that fit, what the business problem was, the problem formulation, us data sourcing from historical data and profile data about where they landed, processing, model training, evaluation, any other questions there? Good. Okay.
Sorry, just a thought. I thought it was interesting that the feature engineering is in the model tuning stage. So I think I'm used to seeing that in data pre-processing.
Me too. I think it happens in both, actually. I think what happens though is that sometimes you're going to do some feature engineering and data pre-processing. And then what will happen is that you're going to run through the model, and then you're going to realize that you're going to run data through the model, do some training, and you're going to realize, oh, you know what? Maybe we need to switch this up a little bit, especially if you're not in the visualization stage,
Mhm.
which is they're going to talk about that there as well. The main point was just to show that when you're following this model, right? If it's not really meeting the business goals, then you have to go back and look at your data. You have to look at your model, and you have to look at the optimizations for how the model is learning.
Mhm. That makes sense.
But you're right, Angela. Most of it should happen in pre-processing. Good. All right. Okay. Now, this is the part where, ostensibly you would choose the project you'd like to work on, refer to your module. Notice it says team. We're not doing that. Here's what's going to happen. Unless it gets really busy, typically what I'll do is that we'll all stay in the same Zoom room while we're working on the labs and subsequently the projects. This is very useful, by the way, extremely useful, because you all will typically answer each other's questions. Didn't always have to happen that way. It's not like I don't want to participate, but it is nice to kind of watch, especially since you all work for the same company, to have you answer each other's questions, because then you'll also, by the way, be able to connect with each other after class. If things start getting noisy, which has only happened like once, and I say noisy, I'm not diminishing anybody's contribution. It's just like if all of a sudden it gets really active and people are like, I can't really focus, which has happened. Sometimes what I'll do is I'll let people go into like what they call a quiet room, and people can go out there. Also, sometimes there have been a few teams where it's like, hey, Michael, can you open 3 rooms and let's all of us go into the flight room, all of us go in the recommendations room, and all the rest of us go into the oh my God, I forgot, fraud room, right? The fraud room. I haven't done that in a long time. Most people don't like that because I won't actually be in there with you, because I'll be hanging out in the main room waiting to see if people need help. So, but it just depends, right? So we're going to see how it goes. But I can open rooms at any point in time that you can freely go in and out of if we want to. And if you're someone who really needs hyper focus and doesn't want to be distracted by any even mild chatter, just know that I can open up a room and people can go into the quiet room if they want to. So just be aware that most of the time, that's not a problem at all. The majority of lab time is going to be incredibly quiet, really still. Only every once in a while will people run into problems and there'll be a little chatter, but most people just tune it out. Okay. But I'm here to take care of you. So if you're like, I definitely need a quiet room, you let me know. We'll make it happen. Okay. So choose the project you want to work on. This is the funny part where we select design for the classroom. Then we're going to move to our projects designated area. I wish we could do that. I got to tell you, I feel like I've adapted pretty well to Zoom, but I got to tell you, most of us are zoomed out. Anybody else zoomed out, where they're like tired of sitting in front of a camera and all this other stuff? I kind of miss the classroom a little bit, because then we can draw on the whiteboard and I could give you stickers and yeah, all that stuff, but not yet. Yeah, definitely miss in person. I had somebody be like, hey, Michael, are you ready to travel again? And I was like, I'm not necessarily ready to travel, but I'm definitely looking forward to seeing some folks. So yeah, good. Okay. So general rule of thumb, think about which project you want. Here's a quick summary. So when it comes basically to developing a prediction from data, we know that there needs to be some rules applied to the data. In classical programming, humans derive the rules about the data. In machine learning, you're going to let the basically the algorithm, the model, whatever, like learn the data and learn how to fit the data for a prediction. And then it can be applied to new data for a more well-informed and adaptable prediction. So it's just kind of like a continuing process. 3 categories of machine learning: supervised, unsupervised, and reinforcement. But as I mentioned before, there's actually an additional 11 above and beyond that, all kind of like inductive and deductive and whatnot. So, but mainly supervised is mainly for data that's already labeled. Unsupervised is for unlabeled data. And reinforcement learning is for agents in controlled environments with certain outcomes. And you want to know how to get to the most optimal way to get to the outcome. Deep learning is where you use layers of mathematical input output functions that take input, drive output, and they go through all these iterations and layers to derive to some kind of outcome. They usually use raw data for that, right? And then remember that supervised either comes in binary, multi-class, and regression problems, regression being numerical outcomes, typically predictions, right, of the future. And then unsupervised is mainly used for like clustering, density, anomalies. Reinforcement learning obviously is for trained in different environments. And we talked about like the different stages of the model, which includes business problem formulation, data pre-processing, right? The actual model training itself, then model evaluation, model tuning, and feature engineering, which is like a second step of feature engineering to Angela's point, which I thought was super valid. And then model deployment, right? Those will be the last step. So let's go through a few knowledge checks. So in general, what did I just say was the biggest difference between classical programming approaches versus machine learning approaches to solving problems? So what's the big distinction there? Who makes the rules in these two approaches? Who makes the rules in classical versus machine learning? Okay. Which of the two approaches is more generalizable to a larger set of situations? The classical approach or the machine learning approach? Good. And what did I say was, the one that was basically, if you looked at artificial intelligence and then machine learning, what was the one that was the deeper version of machine learning? And so a really clean subset, and not NLP, but what do we talk about? And it uses these layers, right, of input, output, mathematical functions to feed out to an outcome. Yeah, deep learning. Good. Did I say there was a class on deep learning? Did I say that already? I hope I did. Yeah, okay, good. There's also, just so you know, there's 5 classes that you could take on machine learning: practical data science, the ML pipeline, ML ops, deep learning. Big data is still running, although they were trying to retire big data, just so you know. And there's one more that I just completely forgot. I'm sure I'll remember. Okay. You are given a task to identify employees who are potentially at risk for quitting based on historical data about the company's employees and historical data about their retention rates. If you're trying to basically predict whether a employee is going to leave or not based on historical data, what is typically the type of machine learning you're going to use? Yeah, supervised. What if you wanted like a probability number? It's still supervised, but what would you use if you wanted a probability number to kind of like predict numerically? Yeah, because classification would be super clean. Like, is this person going to leave or are they going to stay? All right. If I want a number, like a probability number, it'd probably be regression, right? Although that'd be interesting. Okay. Movie streaming companies trying to tag each movie as it's added into different genres, and they have tons of historical information about the description of the movie along with other reviewed articles. What type of ML would they use if they wanted to tag a movie based on known genres and they had a bunch of historical information? Yeah, in general, again, scoping a very loose problem, it would be multi-class classification. What if they didn't have any? I'm just kidding. Don't answer that. You probably know, right? It's not gonna. What if they didn't have any historical data? What if they just wanted to group similar movies together based on actual watching of the movies? That'd be so fascinating. That would really be a lot of horsepower. Let's move on. Let's not answer that question. Okay. All right. What comes first? What's the first thing we start with? In any technological problem, hopefully we start with the business problem. Okay. So what comes after the business problem? We figured out what the business wants. Then we need the ML problem formulation. I kind of wish that said ML. I could change it, honestly, but they don't really like it when I edit the slides. So I could say ML problem formulation, but yeah, machine learning problem formulation. And then the next thing we know, right, is, as Mohammed stated, is that we need to get some data preprocessing, some data collection, some integration, right? We need to source our data first, right? And then we're going to preprocess it. And then what happens next? Right? Then we're going to do some training. And I will tell you that I feel like training, evaluation, and model tuning can they can sometimes munge together, right? But then you obviously you're going to continually evaluate the model. Then you're going to like tune it, and maybe hopefully you've done some feature engineering in the first like data preprocessing visualization. Maybe you're going to go deeper on the feature engineering. And then last but not least, of course, as stated, right, is you're going to deploy it. Straight up. Okay. So this right here is the general overview of the path we're going to follow. Any questions about this? Because we're going to have, a small little personal lab on business problem formulation. You're going to have labs on data preprocessing and visualization. You're going to have a lab on model training and evaluation, and you're going to have a lab on model tuning and feature engineering. Questions thus far? Okay. When you come back, I'm going to talk about SageMaker, and then you're going to do a lab on SageMaker. That lab is actually not really part of this whole thing. It's just that you can see SageMaker in action. Like you can get your hands on it, do it through the console, manipulate it, touch, like just so you can like work on it a little bit, right? So you can just get your hands right in there. So I'm going to talk about SageMaker maybe for about an hour, and then we're going to do a lab on SageMaker, and that's pretty much going to be the rest of the afternoon. And then we're going to do some exam prep at 4:30. And then when you come back tomorrow, we're going to do problem formulation, a little bit of exercises on that. But that's what we're going to do for the rest of the afternoon. So currently, as I said, plus or minus 5 minutes, although in this case, it's like plus or minus 8 minutes. We're actually going to go to lunch. So here's what we're going to do is we're going to go to lunch. And this time you're going to come back at 1 o'clock because that's 68 minutes from now. You're going to come back at 1. And at that point forward, we're going to go into the rest of the day. Does anyone have any burning questions or anything to ask before we break for lunch? By the way, I did see some private posts when I got back, so I will respond to them, right? Privately back to you as well. So just know that I'll get back to you immediately about your questions. Okay. Otherwise, I'm going to put a timer up. Come back at 1 o'clock Eastern. So I'll see you in 67 minutes. Have a good lunch, and we'll talk about SageMaker when you get back.